So this is, as Dr. Muhammad said, this is the second part of our presentation last year in Cincinnati. And today we're going to give a presentation about the performance of this Water-Hyacinth ash in a severe environment of elevated temperature and seawater exposures. Actually, this work done by with a collaboration of Dr. Nancy Soliman at MIT and Dr. Muhammad Mahjoub, associate professor at NGIT, and we have other collaborator from Egypt, from Menofia University and National Water Research Center. So it's a collaborative work done over years with those guys in Egypt. So this is the outline of my presentation today. So we're going to speak about a few words on introduction and a brief summary on Water-Hyacinth ash, which I'm abbreviating in WHA. So production properties, strength activity index, and concrete mix design that we used in our experiments. I'm going to show also the compressive and tensile strengths of this concrete containing this WHA. And I'm going to give more attention on the behavior of WHA concrete in high temperatures and also in exposure to seawater. And I'm going to conclude my presentation with some remarks. So most of us know that cement industry are contributing to the environmental, global environmental CO2 emissions by about 5 to 8%. And a few decades, they started to use SCM like fly ash and slag to reduce this effect. But actually, they are facing a problem using this traditional SCM, as most of the coal-based power plants are being shut down all over the world. So they try to think about alternative SCM. And basically, these ones are based on byproducts and waste and bio-based sources. So today, one of these potential alternative is Water-Hyacinth. So I'm going to give you just a brief summary on what is this Water-Hyacinth plant. It's actually, it's a plant grow on fresh waters, specifically in warm regions. And it starts in Latin America, but now it's been growing and come to the States. So started in Louisiana and South, and now it's moved to the central states as well. So just giving you some facts about the problem of this ash. Just to see that 2 plants can produce like 30 plants in 23 days. So it's growing very fast and produces 1,200 plants in 4 months. So 1 plant can, spread very fast, and this can block the waterways and increase the water level in the main branches. And also it can damage the canal walls and increase the water evaporation, especially it grows on fresh water. And this also can decrease the CO2, the oxygen in water. And this is, they estimated the consumption of 1 acre of Water-Hyacinth plant is equal to the consumption of about 40 persons. Of course, it also contributes to a mosquito production, which is not, preferable in these areas. So it's actually, it has associated with some certain problem. And what they try to do with this Water-Hyacinth plant, they try to collect it and try to collect it and burn it in open air. And actually, this was not a good solution, as this contributes to the air pollutions, and it costs a lot of money for doing this process. And on the other side, as I am engineer and I'm construction, specifically a material engineer, who are concerned with cement, and I see that we have a shortage in resources of the raw materials of cement, and also we have a shortage of energy needed for the manufacture of this cement. Given also the CO2 emission problem associated with cement, so I start thinking about what about if we combine this water-hyacinth plant as alternative cementitious materials. So I start my research by collecting these plants as regular collections. So they collected by cranes, and they leave it on the the canals in banks, so to dry up. This can be like 2-3 weeks to dry up, and they collect that, and we grind it. So we heat this dried plant in 2 different conditions. So one condition is open air drying, burning, like traditional one they used eventually. And also I try to burn this plant in a furnace at a controlled temperature of 600 degrees. And the resulted ash from this process, I used it, grind it in LA apparatus, and sieve it on a 200 sieve, a sieve of 200 mesh. So the resultant, I call it water-hyacinth ash. So I started by doing the sieve analysis to see what are the fineness of this ash. So actually I found that the burning of the ash in a closed area produces more fine particle of 12 microns compared to the open air burning of 23 microns. And this encouraged me a lot. So, and I observed 2 different colors. So the closed burning conditions resulted in a light brown, which is good, and the other one, which is burned in open air, resulted in dark gray ash. So we did the chemical analysis of this ash. We found the content of silicon is quite good, and the 3 components, the silicon, the aluminum, and iron, is approximately 50%, which is approximately similar to fly ash and rice husk ash. So this is the second point that encouraged me to continue. However, I have a large amount of LOI, and basically this is contributed to the organic nature of this plant. So I did the SCM on this ash at different temperature, and I found that similar to the fly ash, that it's angular particle, which is porous and has rough textures, and few of these particles are smooth, but the majority of the particles are have a rough surface. So to test any material to see if it is a pozzolanic, pozzolanic or a filler, so we have to run a strength activity index test according to ASTM 618. And if the results are greater than 75%, I mean so basically they use 20% replacement in a mortar samples, and they compare the compressive strength of this 20% to the control. And if the results of the compressive strength is greater than 75%, it means that this is a pozzolanic. If it's less, it means it reacts as a filler. But in this case, I used a different percentage, 5, 10, 15 of the 2 different burning conditions, and I compared to the regular concrete, which is made with only cement. And I select another reference, is silica fume at 10%. So the 7 days and 28 days results showed a very good indication of SAI, strength activity index. So so I continued, as all these are promising results. So we continued our research, and we tried to implement this ash in concrete mixes. So we used 3 different percentage in 5, 10, and 15 for the 2 different burning conditions. So 0 here is donated to burning in air. 600 is donated to burning in a closed oven. So 10% silica fume as a reference, and OBC is another reference. In this study, we used three different aggregate types: gravel, dolomite, and basalt. And so we used a cement content of 300 kg per cubic meter, and we replaced this cement by this percentage: 5, 10, and 15, and 10% in silica fume. So actually, the compressive strength of these mixtures, we run it in both cylinders and cubes, but today I'm going to just present the cubes results, 10 by 10 centimeters. So as we can see from this figure that all of the 5% replacement of WHA is greater than the ordinary Portland cement, which is in the same times is approximately similar to the silica fume, the 10% of silica fume. And we can also notice that the burning in oven air, the water-hyacinth ash made at closed environment is much better than the one burned in open air. And actually, these results are basically due to the pozzolanic reactivity of this ash until a certain replacement ratio, which is between maybe 5 to 10, because after 10 it starts, decreasing the strength. However, it's still more than the control mix. So this is the splitting tensile stress made on cylinder Brazilian test. And again, it shows that the water-hyacinth concrete has a better performance compared to the references. And again, this is contributed to the pozzolanic activity of this ash, and also the filling effect of the water-hyacinth ash too, and the good adherence between the cement base and the aggregates. So these three factors are contributed to the enhanced flexure splitting tensile strength. So now I start to see the performance of this ash in more severe environment. So I start thinking about what is the performance of the concrete containing this ash in a high elevated temperature environment. So I start thinking about that. So I left actually the curing condition which I followed is I cured the specimen between 1 and 28 days in lime water bath at 23 degrees Celsius degrees. And after that, I removed this specimen from this water bath and they left it in the lab temperature until 3 months each. The relative humidity was approximately 50%. And then I start drying the samples just for 1 day at 100 degree. And this just to remove any moisture that can be contained in the specimens. So the curing regimes which I followed is to put the specimen in a furnace and start heating the specimen for 3 hours at 3 different temperature of 200, 400, and 600 Celsius. And after the 3 hours, I left all the specimen in the lab temperature to cool down before doing the compressive strength testing. So I compared the results to the reference. Here, it's some specimens left in the lab temperature without heating. So as we can see here, this is
2 minutes.
Sorry?
2 minutes left.
Okay. So the compressive strength showed that enhanced performance of the concrete containing the ash relative to the ordinary Portland cement. And this is the main observation from these figures that between 5 to 10% of water-hyacinth ash, it was enough to react with all the electrolyte formed in the system basically the etrangite is the weak ingredient in the cement system, and convert all of this to CSH of higher thermal stability. And beyond 10%, the water-hyacinth ash reacted as a filler, as there is no more etrangite in the system. So at a temperature between 100 and 300, so this temperature, high temperature, made a lot of moisture evaporation from the concrete, and this is what they called internal autoclaving, and this resulted in internal pressure on the particle internally, and reduces the porosity, increases the porosity, and transform all any unhydrated cement grains to etrangite. So it remains etrangite of weak nature. So it decreases all the strengths of the materials. Beyond 400 to 600, so cracks start propagating in the specimen. As you can see at 600 on the right hand, there is a lot of cracks start formed. And other observation is that the type of aggregate played some role according to their thermal stability. So they played a role for increasing the resistance of this concrete. So the second part is the seawater, and the resistance here, I selected seawater specifically because it has more ions, not only one ions, so it has multiple ions. And again, I cured the samples during the first month in normal curing, and the second month I leave it in the lab temperature. And here, after 2 months, I start curing, subjecting to seawater. So the first one is a control without any seawater. The second one is a continuous pass of seawater. The third category is dry wet cycles of seawater. So 1 day in lab atmosphere and 1 day in seawater bath. So here is the results that we obtained, and I represent here as a percentage decrease. So this is the effect of seawater and on the compressive strength decrease. So as obviously we can see the wet dry cycles are more severe than continuous immersion, and this basically can be clearly shown by this relationship. So it means the wet dry is more severe on deteriorating the compressive strength of the materials. So actually, this is the water-hyacinth ash reacted better in resisting the seawater effect because it has a densified microstructure with less porosity and permeability, and this prevents any entry of the attacking ions from the seawater. And also because the pozzolanic activity of the ash with the etrangite, so it consumes all the etrangite. These etrangite are weak, as we said, and it can get attacked by any sulfates coming from the seawater. So there is no more etrangite. It means it's more resistant of the materials. And the second reason is, if we remember that this ash has a lot of aluminum, and we can say it's approximately similar to the expensive cement, which is being recommended by ASTM C8045 for marine structure to compensate the shrinkage. The main observation also from this graph, burning in oven is much better than burning in air due to the increased fineness. And of course, the type of aggregate also played a big role because the abrasion resistance of the different types are different. So as a conclusion, we can say the water-hyacinth ash as a cement can be a good candidate for as ASCM. So it adds a value for our waste materials, it contributes to green environment, and it saves a lot of money for in the cement manufacturers and save a lot of resources used for cement manufacturing. A second point is burning water-hyacinth ash in closed oven produces ash with no effect on environment and with high silica content. So I would recommend ash percentage replacement between 5 to 10 as increases the strength in all the condition of curing, normal curing condition. If you subject the concrete to fire, or if the concrete is subjected to any deteriorating ions. Also, the water addition, the Water-Hyacinth ash addition to the normal concrete, as it enhances all these properties because it reacts with the etrangite, and it transforms it to a strong formulation of CSH, and it densifies the microstructure, and also enhances the transition zones ITZ, and this lowering the porosity and permeability. So it's protecting your concrete against any deteriorating effects. So I thank you so much.